See, for the covalent bonds today, they're not much different than the ionic. What little differences there are subtle because it starts out the same. You look up electronegativity difference, you draw the individual electron dots notations, and then you fit them together the way you would fit them together. How many they're going to need to make everybody happy, to give them an octet. The difference is these guys, covalent bonds, we're going to talk about today, they cannot lose or gain. One guy's not losing, the other guy's not gaining because they're so close together. They're very similar. I'm going to use a tug of war as an analogy also for this. But let's first, little 2-minute animation clip here, summarize what you saw with ionic and what you're going to see with covalent. All right, so hit both lights off for me there for a second. And let me do a little summary animation here. You ready?
Ionic bonding occurs between two atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom.
This is what we did yesterday, the day before.
A sodium atom has 1 valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion. Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electron.
Okay, so this is what we're doing today. Notice this is a very short little clip here. It's like a minute and a half long. All right, this is what we're going to do today. This is what we're going to talk about. This is what's happening in the covalent bonds.
The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with 1 valence electron needs 1 additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen and hydrogen atoms collide, covalent bonding is accomplished by the sharing of electrons. By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with the hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still 1 short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.
All right, so you're getting the idea. This pretty much predicts why I told you this. I've been hinting at this for a while. This tells you why. Hit those both lights on for me for a second. This tells you why formulas have the formulas that they have. Why is water H2O? Now you see why. We're going to do water in a second anyway, but you just saw it there. In order for everybody to be happy, oxygen wants 2. Hydrogen only has 1 that he can share. You got to have 2 hydrogens to make them happy. Why is sodium chloride and not NaCl2 or NaCl3? Because 1 sodium makes 1 chlorine happy, and they're good. All right, so that's how you're able to predict formulas. And we're going to get to that and naming names of these compounds also. But let's get covalent bonds first. Hit the front line off. Okay, covalent bonds. This is B in your notes. And we're going to make the same basic kind of charts we made with the ionic bonds. And then we're going to do a lab on Monday. Actually works out well. You guys being the first class, both times are having that class as a double, so that I actually got through with the other class, even in a single, because you guys set things up for them and we were able to do that. Same thing's going to happen on Monday. We'll have that lab on covalent bonds. I will have you guys make 2 covalent compounds. Sometimes you get lost in the middle of the lab. You kind of forget why you're doing it. You don't realize the point of that lab yesterday when we burned magnesium? Do you realize what we were doing? We were taking pure magnesium, Mg, adding it to oxygen from the air, Mg and O, making magnesium oxide. That's what you also wrote on your paper. Okay? Anyway, let's get to covalent bonds and what they are. A covalent bond is formed when electrons are shared between atoms, as you just saw in the little video clip. Neither guy is strong enough. I think I used this analogy the other day about a tug of war, or did I in this class? No, maybe I didn't. Okay, well, I'll use it now. If you think of a tug of war, let's say we've got one guy who's really, really strong. Like, I don't know, who's the strongest guy on the football team? Stout. Let's say Stout is up against Haley in a tug of war. Okay? Now, Haley's going to put up a good fight, but it ain't going to be enough. And Stout's so much stronger than Haley, he'll probably rip the rope right out of her hand. That's an ionic bond. Really strong guy, and not so strong, no offense, Haley. Now, let's say I've got two guys who are of similar strength, like, say, Stout and me. Not really. Let's Stout and somebody else who's also fairly strong. Well, but one guy's going to win, and if you say he's the strongest, then he'll win. But he's not going to be strong enough to just rip that rope right out of her hands, right out of the other guy's hands like he can out of Haley's. That would be like a covalent bond, but a polar covalent bond, where they're sharing, but he's going to pull the rope closer to him. He's never going to let go, but he's going to pull it closer to him. Let's say, for some god-awful reason, we decided to clone Stout, and we made another Stout. And they were of exactly the same strength. And they were having a tug of war. Well, they couldn't move the rope then. It would just stay there. And that is like a covalent bond that's nonpolar. So those are your three options. Ionic, two very different guys. One's very strong, one weak. Covalent, polar, different, but one guy's going to win, pull the electrons closer to him and around his nucleus more often. And finally, identical atoms, or very, very similar atoms, where you're not going to really move those electrons. All right, so a covalent bond sharing electrons. And compounds with covalent bonds are called molecules. Because neither one can rip the electrons away from the other guy. They have to share. And we call these guys molecules. You know, it's not technically accurate to say we have a sodium chloride molecule. All right, because sodium chloride doesn't really form a molecule. That's an ionic bond. It forms an ionic crystal. It is technically correct, however, to say we have a water molecule. Water does form molecules, because you just saw it a minute ago, because it has covalent bonds. All right? Okay. Now, as I told you, there are two types. And I already kind of illustrated them both with the tug of war analogy. Polar covalent, and we already got these numbers down yesterday, the day before, whatever. 0.4 to 1.7 is going to be classified as polar covalent. If it falls right on a borderline number, which it won't, but if it does, you have to remember, these are just cutoff points. In reality, guys who are right on those numbers may have properties of either polar or nonpolar or ionic, depending on what number they're near. There are guys who are considered ionic bonds, but aren't at 1.7. They're actually at 1.6 something. Potassium bromide, I think, is an example of that. And there are other guys who may be at 0.4, but are considered, or above, a little bit above 0.4, but are really kind of mostly nonpolar. So they're just cutoff points. One atom in a polar covalent bond pulls the other atom, like a tug of war, where I got two guys of unequal strength but pretty close. One atom pulls those electrons closer to him. Actually, it's not really about closer. It's more about how much time it spends around the nucleus. It's going to spend more time around the guy who's more electronegative. The stronger guy. You know where the strongest guys are? The stouts are. Where are the stouts in the periodic table? They're the guys in the upper right-hand corner. They are the most electronegative elements, like fluorine, oxygen, chlorine, those guys. Very strong electronegativities. All right, let's do some examples. Okay, just the same kind of chart we had before. Oh, again, there's a little picture. I don't really like, I didn't show you what's easier. I don't really like to give them those rings. I hate rings. I think what you saw before, the little animation was better than that. All right, let's do the same exact chart. Remember, make these charts, the first three, very, very small. Most of our room is needed for the Lewis structure. Let's use hydrogen and chlorine for our first example. Very easy one to do. I bet you could probably do this, guy, having just watched the video and having heard me explain it. I probably don't even need to do this. It's that easy. But we'll do it anyway together. Look at the difference. You need the polarity charts. You need the electronegativity charts. Get them out. What's the difference between H and Cl? Cl is 3.00. What's H? 2 point something? What do you see for a difference? 0.80? 0.80? Okay. What does that make him? What kind of a bond is he going to be? 0.80? Where does it fall? Polar. You can abbreviate on your charts too. You can just call them polar covalent. PC. Politically correct. PC. All right. Polar covalent is fine. Now, let's draw each one separately. H, he has one dot because he's in group 1. He has 1 electron in his outer shell. Cl, he's got 7 in his outer shell. He's in group 7. You can tell that. He's got 7 dots in his outer shell. And you just saw one kind of like this. What's going to happen here? Well, here's what's going to happen. I know what you're thinking. If you're thinking of an ionic bond, you say, okay, he's going to lose and he's going to gain. But that's not what happens this time. And here's the reason why. Hydrogens and chlorines electronegativities are so similar, they're only different by 0.8, that neither one's strong enough to rip the electrons away from the other guy. So they have to share. They're going to have to share. And that can accomplish pretty much the same thing by sharing. Because watch what happens if I redraw this guy with him sharing these electrons. I can redraw it, and remember, I don't have to draw him up here. I can draw him on a straight line. If I draw him like that, notice how everybody actually has what they want. And notice how it's drawn differently than the ionic bond was. Do you see any charges on there? And you shouldn't. If you end up putting charges on there, you're losing points. Because a charge means that he lost or gained an electron. Nobody lost or gained an electron here. Do you notice they're written halfway between? Last time I made sure you put all the electrons of the guy who was gaining, all of them around him, and none of them around the other guy. Here, they're written halfway between. Okay? All right? Now, how is everybody happy, you say? Well, let me show you. Don't have to do this. Don't do this. Why is chlorine happy? Well, chlorine, even though this electron is coming from hydrogen, is not spending all of his time around chlorine. He is spending some of it, and it's kind of like he's got an octet from him. Hydrogen doesn't have an octet, but remember, hydrogen is one of the few guys who doesn't want an octet. Look where he is. He only has 1 electron. What's the nearest noble gas to hydrogen? Helium. He wants to be like helium. He wants 2. And if he shares an electron with hydrogen, or chlorine, he'll have 2. So he's happy, and he's happy. Everybody's happy, happy, happy. Right? Okay. Let's do another one. Oh, by the way, I am going to ask you to do this sometime, especially when it comes to, I may as well start doing it right now. There's a couple of things you could write this differently. One is, instead of writing, a lot of times electron dot notations, instead of them writing the pair of electrons that are shared, we could write a shared pair of electrons as a dash. So it would look like that. Okay, so rewrite that underneath, just so you see. A dash means a bond, shared pair of electrons. And another thing I want you to do on some of these. On some of these, especially when we're going to talk about intermolecular forces in about, the middle of next week, it's going to be important who's pulling harder. Who's more electronegative, H or Cl? Cl. So I'm going to draw an arrow towards the guy who's pulling harder. I want you to do that for the polar ones. And what you do with this arrow is you actually make the other end of the arrow a positive. Now, that's not a positive charge, but it's showing you which side is going to be slightly negative and which side is going to be slightly positive. That's going to come into play when we talk about intermolecular forces in Wednesday or Thursday next week. This side's a little positive. You know why? Because chlorine's pulling those electrons more towards him, so he's got a little bit of a negative here, a little bit of a positive here. Don't write those down because I don't want you to think that they're actually ionic. They're not. But there's a little positive on this side of the atom and a little negative on that side. All right, let's do the next one. Let's do this guy, which you just saw done in the video pretty much. Do this one on your own, H and O. Look him up, and this one will not be a 1-to-1 ratio. Figure it out. And wrote H like that. This one I'll, just for fun, a lot of times I like to do this. I'll make H red, and I'll make O blue. You don't obviously have to do that, but just showing you what happens here. And what's going to happen is, how many of each do I need to make everybody happy? Hydrogen only has one to share. Oxygen needs how many? 2. So what am I going to need? I'll need 2 hydrogens, right? Then when I go and write my hydrogens around oxygen, let's do the oxygen first. Okay? You'll actually learn in Chem 2, not in Chem 1, about shapes of molecules and why they have a particular shape. For now, I wouldn't care if you wrote this HOH. I really wouldn't care a whole lot. All right? But you saw the, which is ho. Yes, that's right. It's a ho, 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 like Santa. What were you thinking? What were you laughing at?
Head of household.
Head of household. Seriously. That's pretty good. Seriously. How many of you guys thought of head of household? Look around. No one. That's pretty good, though. I like that. I was thinking of like Santa Claus. Sandy Claus.
Yeah.
Big Brother?
Yeah.
Head of household? Never saw it. What is Big Brother? Reality TV?
No, it's a game show.
Oh, game show. Okay. There was a Big Brother reality TV thing, isn't there? Or wasn't there?
It's kind of a game, kind of reality. You could
Is it?
interpret either way.
And some heaps of heroin.
Heaps of heroin? That's what... Okay. Jeez, whatever happened to the innocence of ho, ho, ho?
They
Oh,
died 7 years ago.
anyway. If you think of it this way, you don't have to draw it that way. If you drew it that way, it wouldn't be wrong. If I draw it like this, it wouldn't be wrong either. Okay? And that just shows you that the electrons, again, I don't need colors, but the electrons are being shared. Because once they get together, it's not like this electron was hydrogens. Hey, that's mine. Don't give me that back. They're all electrons and electrons. Okay? They're all the same. Notice there are no charges, and notice they're written halfway between. Last thing I have to do is put my little arrows. Did you put the arrows on? Which way are the arrows pointing? Towards the oxygen. See it? Now, again, those arrows are not necessary to do a Lewis structure. However, they are going to be useful for us when we start talking about intermolecular forces, especially dipole-dipole attractions. Okay, we'll talk about that later. All right, there you go. There you have it. That's all we're doing for polar covalent. Let's do nonpolar quickly, and then I'll let you start on the homework. Nonpolar covalent, no big surprise here. 0 to 0.4. We already saw that. And I bet you already know what I'm going to say about how they're sharing electrons. How do these guys share electrons? Remember my cloning?
They don't.
Equally. They share them equally. They share them very well, actually. Neither guy is stronger than the other one, pretty much, for the most part. If it's less than 0.4, you assume that there's not enough of a difference to make these guys spend any major amount of time around one guy's nucleus more than another one's. Let's make the same chart for nonpolar ones, and you're going to see something interesting about some particular nonpolar ones, okay? Same chart. We'll start off with C and H. Look the difference up. It's going to be less than 0.4, but not by much. I think it's like 0.36, isn't it? Is that right? Or am I wrong? 0.36? Okay. All right. And that makes him... What should I write here? If I wanted to abbreviate it, what could I do? NPC. Not politically correct. And not head of household. I don't know where that comes from. Seriously. Big Brother. You got me on that. You know where Big Brother comes from, of course, the phrase. What book?
It's from my George Orwell, correct?
Yes, George Orwell. Which book?
Something with a 2.
No?
It's more when they're like Big Brother is watching you.
Right.
It's like the utopian society.
Right.
That's watching everything.
It's a date.
1984.
Thank you, 1984. Very good. Wow. Nice. By the way, not a big fan of that one. Better George Orwell book. Definitely. Which one? Animal Farm. Great book. Okay. Lewis structures. How do I draw these? Same as I did before. C with his dots around them. Right? Now the thing about, I'll tell you right now with carbon. Right? Stop right there. You won't learn why until Chem 2, if you take Chem 2. But Carbon we would normally draw like this. Watch. We'd normally draw carbon with, as the S fills up and then a P and then a P. But it turns out that when carbon forms bonds, something called hybridization happens. You remember how things hate to be half filled, like not like in between. They want to be either full or half filled, okay? Well, it doesn't like this at all. So it ends up, when it forms a bond, hybridizing its orbitals all together, kind of mashing them together. We'll talk about that in Chem 2. So when you draw carbon with its 4 electrons, you can actually draw him like that. Think of him that way. It makes life a lot easier. Again, in Chem 2, we'll find out what's going on more there with the orbitals and stuff, but for now, it's not important. Yes, we all would have drawn 4 electrons. The question is where you would have put them. I'd suggest you put them like that for carbon or anybody in a group 4 element. Now, I'm going to add to him hydrogen to make everybody happy. See, the reason I had to draw this way, it's a little bit easier to see what you need to make everybody happy now, don't you? Isn't it? What do you need to make everybody happy? 4 what? Hydrogens, yeah. It's a little bit easier to see that when you draw carbon like that. So I need 4 hydrogens to make everybody happy. I draw them over here. How will I put them around them? Remember what I said yesterday? I made sure I did this before you started the lab yesterday, remember? I cannot just do this. Can't do that, right? Can't put them all in one line. I got to show who's sharing the electrons. So I'm going to do this. I'll draw, who should I draw in the middle? C. Is that like Spanish for yes? Multilingual. CC. All right, C in the middle. Then what? H everywhere, right? Got it? Look good? That's it. Draw. Or did you already draw it? And you obviously cannot fit, as I see Anthony trying to make lines across this way. You can't fit all that into one line. Use space. Don't be afraid to use some space here. Okay? All right. How are these guys different? How are these different than the polar covalent ones? Well, they're not much different. They're written halfway between. But what are we not going to draw on here? No arrows, because nobody's pulling harder than the other guy. All right, let's do a couple more. Try F and F by yourself. I don't know why this causes problems. I would have thought this would have been a very easy problem. But when I finally realized that I've been using a lot of H's, and if I don't, I added this one on because if I don't do this one, people have problems with this. They see it and they can't do it. So let me see if you can do that one on your own. First of all, what's the difference between F and F? 0. And you might say, well, is that going to form a compound with itself? Yes, it does. And I'll explain why. They're called the diatomic elements in a little bit. Now, this guy wants 1. This guy wants 1. And they have one place where they can share. How will I draw this guy? I'll just draw him like this. I do not need to do that. I was just saying before, it doesn't matter how I write them at this point. That's the answer. That's all it is. It's just that. I don't have to show, oh, there's a top and a bottom or whatever. I've got to flip this guy like that. It is like a puzzle. You can think of him like a puzzle to give everybody 8. You can. But when you go to write them, it doesn't matter when they form a bond about those electrons. Okay, how you draw them in. If you were to think of all these guys like it showed you a minute ago, some of them were X's. These are all X's. Whoops. That would be nice. And these are all O's. The fact that a minute ago up here is where you had the guy, and this one was up here, it doesn't matter. You want to be able to show that they're sharing them, so you draw it like that. And that's all you have to draw for that guy. All right? Now, I've got one more problem for this. This last one I'm going to do. I'm going to wipe the board up here, and then you'll be able to start on some problems. And he is going to be tricky. This is a tricky one. There are actually rules that govern these. And there's actually rules you could use and tricks you could use. But I'm not going to go into too much detail in these electron dot notations. When you try O and O, when you try to do oxygen with another oxygen, because there's something I haven't really pointed out to you yet, what could happen with these guys. So it's not really your fault. Try drawing those guys put together. This is the last one I'm going to do as an example. I'll draw the correct answer up there, but I'm going to draw some wrong ones down here first. Now, everybody got an answer? Come on. Come on, Marie. Come on. Okay, it's not like you can't draw. I love when people do this. Oh, he just said it's going to be tricky, so I can't even attempt it. There's no way. That's not true. You certainly can attempt it. If you get it wrong, I wouldn't be surprised. But it doesn't mean you have to have a blank piece of paper staring at you right now. You know what to do. My guess is the most common mistake will be this. Now, why is that wrong? Who can tell me why that's wrong?
You're sharing two places.
No, not at all.
Because you just magically gained electrons.
That's the reason it's wrong. Because I magically gained electrons out of nowhere. How many total electrons are here? 2, 4, 6. 6 plus 6. And here I've got 2, 4, 6, 8, 10, 12, 14. What is 6 plus 6? Does 6 plus 6 equal 14? Equal 14? No. So I magically gained electrons. That violates the first law I ever taught you in this class. The law of what?
Conservation.
Conservation of matter and energy. You can't create or destroy matter or energy. You can't create or destroy electrons either. All right, so that's wrong. Well, I know what I'll do. I got to get rid of 2 electrons, right? I'll erase 2 electrons. Ta-da! All done. What's wrong with that? It's not right. Don't write it down. I'm being facetious. What's wrong with that? Neither of them have an octet. This guy's got... And I just erased it. There you go. Hold on. Okay, that's what you look like, right? Okay. 2, 4, 5, 6, 7. 2, 4, 5, 6, 7. Smiley face. Angry smiley face. 14 for a mouth. I don't know. It's not a donut. All right. It does look just like a donut for Homer Simpson would eat, doesn't it? 2 donuts together. Homer would be eating those. They like to put sprinkles on it. You're completely lost now if you weren't before. All right. Let's fix this. So, as you just saw, Homer Simpson likes donuts. Now, as you just saw, I can't do that either. I can't do that because if I erase 2 dots to make the things add up to be 12, I don't have an octet for both of them. Here's your solution. I'll bet you nobody thought about doing this. What?
2 oxygens.
No, I can't give one guy an octet and the other guy not.
3 oxygens.
I can't. 3 oxygen will just make the problem worse.
Share 2 places.
But I can share 2 pair of electrons. Watch.
You know
Watch.
this.
Watch. What? Let's draw these. Watch.
Now you're making. Let's stack them together.
Let me draw these again using colors. Okay? Ready?
Yep.
Watch. I'll use red
For oxygen and blue for oxygen.
and then blue for the other oxygen.
There's 6.
Very good. Now, when I put these guys together, I'll draw my 1 O over here.
Don't do it.
Okay? And I'll draw my other O over here. I'm not going to touch these guys here, right, correspond to these here. These guys here correspond to those there. And I'm going to share these electrons between both of them. I'm going to make them in black. Okay? That solves both problems. Draw that. You don't need colors. Just draw that as is. I'll show you why it solves both problems after you draw it.
My way worked fine.
What, you just add an extra oxygen?
Yeah.
It doesn't work. That's ozone. That's O3. It's not oxygen. All right, you ready? Here's why this works. Total number of electrons. 2, 4, 6, 2, 4, 6, 12. 2, 4, 6, 8, 10, 12. Didn't violate that. Watch. Does he have an octet? Because remember, these are both being shared. Both pairs are being shared. He has an octet. The ones that are written in between are shared electrons. Okay, that's why I didn't draw them as red or blue. These guys are being shared. Okay. Now, again, in reality, these electrons, once they're forming a bond, they're kind of like all over both guys' nucleuses anyway. But that's how you have to think of it.
What's up?
Not much. I'm almost done.
Right,
1 second. Got any more of those?
No, they're all empty.
What?
Everyone's ate them all up.
All right. So this is how you would draw oxygen, and that is called a double bond. The way you would draw that would be like that. I mean, you obviously could leave it like this, but those remember the bonds mean a shared pair of electrons. I could have done that for the other guys too. The fluorine could have been like that, and the carbon and hydrogen could have been like that. Carbon and hydrogen would have looked like this. A dash means a pair of electrons. Okay? All right. Now, these last two guys may seem strange to you. Oxygen and fluorine. Why would they form a bond with themselves? Well, it turns out they are extremely electronegative. And there's other guys like him. I bet you Allison knows what they are. What are the elements that are so desperate for electrons that they will form a compound with themselves? The diatomic elements. What are they?
Brinkelhoff.
Brinkelhoff! Exactly.
Fluorine, oxygen, nitrogen. What's the Hoff? H.
Yeah. These guys on the periodic table. You see a 7 over here? It looks like a 7. NOFCLBRI. Looks like a 7. It's a 7! Have you ever drawn a 7?
It's a sideways out.
Oh, okay.
Okay. It's a 7. Well, there are 6 of them there, and the 7th one is hydrogen. These guys are so desperate for electrons. If they're sitting there by themselves, they've got to have an electron. So even if there's nobody else around, they're going to get one from themselves. They are called, well, yeah, they are called the diatomic elements, or you can remember them as Brinkelhoff. Sergeant Brinkelhoff? Hogan. That's from Hogan's Heroes.
What's the sunburn?
This is just it really is not under any topic. It's just showing you their. We're actually going to come back to this again in a couple of chapters. It's going to be very important. But those are the guys that will form non-polar covalent bonds with themselves and no one else around, even if there's no one else around. So what I'm saying is, you'll actually get, like, when BR is just a jar of BR. Jar of BR. All right. Anyway, it would be BR2. There's going to be 2 of them bound together. Okay. And iodine, and not every one of those is going to bond with itself. They are so reactive. They're so desperate for electrons. If there's no other electron, if there's nobody else around to get one from, they will have to share with themselves. They'll have to make do.